Myself, A.N. Surde, Assistant Professor, Mechanical Engineering Department. Today, we will discuss about the Kleins construction diagram. At the end of this session, students will be able to determine the velocity and acceleration of reciprocating parts in engines. So, consider a single sided crank chain mechanism where OC is crank, PC is connecting rod, and P is the piston. The crank OC makes an angle theta with the inner dead center. So, with the help of Kleins construction, first of all, draw a perpendicular from point O in such a way that when the connecting rod PC is extended, it will intersect this perpendicular at point M. So, first of all, draw a perpendicular to OP from O and then produce the connecting rod PC in such a way that it will intersect the perpendicular which is drawn through point O at point M. So, triangle OCM is nothing but it is a velocity triangle. In figure A, the relative velocity triangle is shown. So, triangle OPC is the velocity triangle where vector OP represents velocity of piston with respect to fixed point. Vector CP represents velocity of P with respect to C, and vector OC represents velocity of C with respect to O. So, when this particular velocity triangle is revolved through 90 degree in anticlockwise direction, the triangle will be triangle OC1 P1. So, this particular triangle OC1 P1 is similar to triangle OCM, where this OM is perpendicular to line OP. CM may be regarded as parallel to PC and OC may be regarded as parallel to OC. Hence, triangle OCM and triangle OC1 P1 both are similar. Therefore, vector OP1 is parallel to OM, vector OC1 is parallel to OC, and vector C1 P1 is parallel to CM. Therefore, using similarity properties of the triangle, vector OP1 divided by OM is equal to vector C1 P1 divided by length CM is equal to vector OC1 divided by OC is equal to omega, where omega is angular velocity of crank and crank is rotating in clockwise direction. So, vector OP1 in the velocity diagram represents the velocity of P with respect to O. So, VPO divided by OM is equal to vector C1 P1 represents velocity of P with respect to C divided by CM is equal to vector velocity of C with respect to O divided by OC is equal to omega. And therefore, velocity of piston P with respect to O is given by omega into OM, whereas velocity of P with respect to C is equal to omega into CM, and velocity of C with respect to O is omega into length OC. So, by using these relation, we can determine the velocity of various points with respect to another link. Now, in order to construct the acceleration diagram, first of all, take radius equal to length CM and as C as a center, draw a circle. So C as center, radius equal to Cm, draw a circle. Then PC as a diameter, draw another circle. These two circles will cut each other at 2 points, that is point K and point L. So these two circles will cut each other at point K and L. Hence, join point K and L in such a way that it will cut the connecting rod at point Q and line OP at N. So this line KL cuts the line PC at Q and line of stroke OP at N. Therefore, quadrilateral CQNO represents the acceleration diagram. Now, in figure 2, the acceleration diagram is shown by relative velocity method. So, from the acceleration diagram, O dash C dash X P dash is parallel to quadrilateral CQNO. So, vector O dash C dash may be regarded as parallel to OC, which is equal to vector C dash X is also parallel to CQ. Then vector X P dash is parallel to QN and OP dash is parallel to ON, which is equal to omega square. Now, from the acceleration diagram, vector OC dash represents the radial component of CO. So, radial component of CO divided by OC. Similarly, vector C dash X represents radial component of PC divided by CQ, which is equal to vector XP dash represents the tangential component of PC divided by QN, which is equal to vector O dash P dash represents acceleration of P with respect to O divided by ON is equal to omega square. And therefore, from above equation, we can calculate the radial component of CO, which is equal to omega square into length OC. Radial component of P with respect to C is equal to omega square into CQ. Tangential component of PC is equal to omega square into length QN, and acceleration of piston with respect to fixed point is equal to omega square into ON. So, by using these equations, we can calculate the acceleration of various links. Now, if D point is the midpoint of the connecting rod, then velocity of point D that can be determined by locating point D on Cm, because as point D is lying on link PC, the PC is parallel to Cm, hence point D1 lies on Cm. So, the ratio in which point D divides the link PC, in the same ratio the point D1 divides the Cm, and therefore, as point D is the midpoint of PC, D1 will be the midpoint of Cm, and hence locate point D1 on Cm. Join OD1. Therefore, velocity of D is equal to omega into length OD1. Similarly, the acceleration of point D also we can determine. Now, in the acceleration diagram, the vector C dash P dash, which gives the total acceleration of link PC, and hence in Kleins construction diagram the line Cn, this line Cn will give the total acceleration of link PC. In order to determine the acceleration of point D, first of all draw a parallel from point D parallel to OP from point D, which will cut the line Cm at point D2. So join OD2. Therefore, acceleration of point D is equal to omega square into length OD2. Hence, by using Kleins construction diagram, we can determine velocity and acceleration of various links without drawing the relative velocity diagram. The material is referred from the book R.S. Khurmi Gupta and S.S. Ratan of Theory of Machines,